Hey guys, today in class we learned about thin film interference. Definitely missed seeing all your lovely faces in class today. Y'all bring a lot of life. We were a little dead. Also, if you're rewatching this and you were in class, you were a little dead. So thin film interference happens because of a phenomenon called partial reflection. And partial reflection is based on the idea that if you've got a reflected surface, sorry, that was not a pencil. I need a pencil. There's a reflected surface. All right. If you got a reflective surface and light goes onto it, two components of light come out of that. You've got most of it going and reflected back, but you'll also have a small part of it that goes through, and that's called partial reflection. Part of it gets reflected, part of it goes through. And any reflective material has some thickness, T. So it's got a back of the material, and the little bit of partially transmitted light will get reflected at that point to go join the rest of the light on the outside. And that's called partial reflection. It leads to some distortion in mirrors. Like here you see you've got a candle that's got a distorted, blurry set of two images where you can see the candle. And that happens because you've got partially reflected light that comes off the front of the mirror and partially reflected that goes off the back of the mirror. This phenomenon also occurs in things called thin films. So a thin film is a slightly reflective surface that will reflect part of the light, transmit part of the light, and then have it reflect back out. So it works exactly like the example we were just showing. A couple of things to note before we go into all the details are that as light goes from air into the thin film and into potentially a third medium, it's going to change wavelengths. The frequency is going to stay the same, but it changes wavelengths, so it reduces in speed according to its refractive index, which is N. So each different medium will have a different refractive index that changes its wavelength, changes its speed. And the other idea that you need to consider is that when light is reflected off of the front of the surface, it creates a wave pattern. And then again, when it's reflected off of the back, it creates a different wave pattern, or a separate wave pattern, I guess you could say, not necessarily different. And those two wave patterns are going to overlap, which means they're going to cause some interference. And that interference can either be constructive to generate a brighter light, or destructive, which will generate no light. And whether or not they constructively or destructively interfere is based on their phase. So wave phase is basically how far through the cycle a wave is. So if two waves are in phase, I'm going to do a red wave and a blue wave. This is a red wave. Okay, there we go. And a blue wave. If they are matching, their crests line up, their troughs line up, everything's the same frequency, the same wavelength, and they are in line where the crests match up and the troughs match up, that is in phase. Okay, and they are going to constructively interfere and cause a brighter light. But if we've got one that is out of phase and perfectly out of phase, it's going to be the exact opposite wave. So where you have a trough on one, you'll have a crest on the other, crest on one, trough on the other, and vice versa. And if you add those together to get a resultant wave, it is just a flat line. They cancel each other out entirely. So sometimes the reflections will overlap and create a brighter light, but sometimes they will overlap and cancel each other out, so you won't see a reflection at all. And this is based on how in phase or out of phase they are. So what we're essentially looking at is the phase shift or the phase difference when the light emerges from the thin film, to see if it's going to be the same as the phase of the first reflected light or if it's going to be different. And the conditions for that are listed here, but I'm going to kind of derive them over here via some pictures. All right, so this is going to be my thin film. Oh, I don't want to draw it in green. I want to draw it in black. All right, this is my thin film. Okay, perfect. And I'm going to have some, let's say, green light coming in. Green light is coming in. Now that green light is going to be split into part of it that gets reflected immediately. That's going to be the yellow part. That gets reflected immediately. But there's also going to be a blue part that goes in, hits the back, and reflects off of that. Okay? So the light splits, and part of it bounces straight off the front of the mirror, part of it goes to the back and bounces off from there. So my yellow ray is going to have a different total path length than my blue path length. If you see, my blue arrows travel further than my yellow arrow to get to the same spot. I guess my blue arrow doesn't go quite to the same spot. I'll make the blue arrow go to there. So they each go some distance. We'll call the distance L for path length, okay? So yellow has a path length 1 and blue has a path length 2. So what we're going to be interested in is the difference in path length. And that difference happens right here in the picture, okay? Where the blue partially transmitted light goes through the mirror to the back and bounces back again. Now, if the mirror has a certain thickness, T, that extra distance is 2 times T. So the yellow wave is going to go 2T less than the blue wave, or the blue wave is going to go 2 times the thickness more than the yellow wave. And while it's traveling that distance, it's going to be oscillating back and forth a certain number of times based on its frequency and its wavelength, which we could calculate in the material if we knew its index of refraction. And it goes in at a certain phase, at a certain point on the wave, and it comes out on a certain point. Now, if we want these things to constructively interfere and add together, that means the blue wave needs to enter and exit the film in the same phase it was already in, which means it needs to have gone an integer number of wavelengths, which is going to be m. M is just an integer times its wavelength there in the film. So the distance it travels has to be integer number times wavelength, and the distance, the extra distance it travels, is 2t. So you get the condition that 2t path length equals m times lambda, which is the wavelength inside the material. However, if you wanted it to be destructively interfering, you would have to go into the material in a certain phase and go out of the material at the exact opposite phase. So you'd be in the opposite phase. To put something in an opposite phase, you have to move it by 1/2 wavelength. So we would make destructive interference 2t equal to m plus 1/2 lambda. That moves it out of phase that sets the condition that our wave has to exit the film 1/2 of a wavelength out of phase from where it was, which is going to be exactly out of phase with our yellow ray that just reflected off and didn't go through the film. So essentially what we're doing here is saying that the path length that the wave travels through the film has to be equal to m times its wavelength, where m is any integer for constructive interference, and it has to be m plus 1/2 lambda for destructive interference. However, there is a hang-up with this, and you actually can't see this on this video because my software doesn't do it, but you can go look in the slides at this animation, and what you'll see is that the wave travels along, going down the string. Okay, this is like the wave translating that way. Now once it gets to the end, it will flip down to the bottom, and you can see this in the animation on the slides if you want to. So sometimes when a wave travels down to the end of the line, wherever it's going to reflect off of, it will flip. And there are specific conditions for why that happens. With strings, it's based on tensions, but with light, it's based on the index of refraction. And so the condition is that if the index of refraction for the reflective surface is higher than for the incident surface or the incident medium, the wave will flip. So if we have light going from air to glass, air's got a refractive index of like 1, glass is about 1.5. So when light bounces off the glass, since it has a higher index of refraction, the wave will flip and then bounce back off. And so we need to compensate for that in our math. And the way we do that is by instituting a phase change. So a flip is basically a phase change for the wave. And to flip a wave or put it in the opposite phase, you have to change the phase by a half length. And we will do that by, for the path length of the wave, anytime we've got a wave following a path length, if there's a phase change, we add half of a lambda to the path length. So if you've got a thin film where we're reflecting, and say this is an index of 1.5 and this one's index of 1.6, right there we'll have a phase shift or phase change. So your path length, instead of being 2t, is going to be 2t plus 1/2 lambda, which is the wavelength inside the film. All right, that was a lot of information, and we're going to take it and compile it here for this example. This example says to keep unwanted light from reflecting from the surface of eyeglasses or other lenses, a thin film of material with an index of refraction n equals 1.38 is coated onto the plastic lens, which has an index of refraction of 1.55. And the question is, what is the thinnest film that will minimize reflection for this specific wavelength, 550 nanometers, which is the middle of the visible light spectrum? All right, so we are going to look at this. I'm going to make the problem small. First thing we want to do is draw a picture. We're going to have, this is our thin film coating that goes on the glasses. This is going to be the plastic lens. And then this over here is going to be air through which light is traveling. So light is going to go here and reflect off. And then some of it's also going to go into the material and reflect back out there. First thing we need to do is find the path length that the dotted line travels as opposed to the path length that the solid line travels, based on the thickness and the phase changes. So the thickness of the material, we're just going to give as T. Path length equals 2 times T, because we're going through that thickness twice there. All right, but then we also have to consider phase changes. So at this interface, let's see if there's a phase change. We know index of refraction of air equals 1. It says the thin film has n equals 1.38, and the plastic lens has n equals 1.55. And the condition for phase change is that N2, the one that's going towards or reflecting off of, has to be greater than N1. And if we look at this reflection here, N2 is greater than N1, so there's a phase change, which means this initially reflected light goes through a phase shift of 1/2 lambda. And then our other reflection happens right here. Our transmitted ray reflects off this surface. N2 is greater than N1, so there's also a phase change there, adding 1/2 lambda. And since we're looking at the difference in phase, we do the path length of the dotted line, 2t plus 1/2 lambda. minus the path length of the not dotted one, the initially reflected one, minus half lambda. So the half lambdas cancel out and go away. So our path length ends up being just 2t, which makes sense because if both waves are flipping, then really the whole thing is trivial and you just have to consider the thickness of the film. All right, then we have to set that equal to either m times lambda or m plus 1/2 times lambda. And that's based on constructive or destructive. Now, if we look at the question, it says we're keeping unwanted light from reflecting, and we're trying to minimize reflection. If we're minimizing reflection, that is destructive interference, which is this bottom doodad here. So we say that 2 times the thickness has to be equal to m plus 1/2 times the wavelength. But that is the wavelength that is inside the material, okay? Wavelength in here. We'll call it wavelength 2. Wavelength out here is wavelength 1. So we need to calculate wavelength 2. We have wavelength 1 equals 550 nanometers. You can use indices of refraction to find our lambda 2. If you say index of refraction equals C over V, and out here where the index of refraction is 1, your velocity is simply the speed of light, or c. We also have this equation that says velocity equals frequency times wavelength, or wavelength times frequency if you write it the weird way I just did. And we can plug that in for each part of our equation. We say that the frequency times the wavelength of our light going at the speed of light is divided by the frequency times the wavelength of our light in the second area. But we should know that frequency stays the same. Sorry, that's the bell for lunch. Frequency stays the same throughout the entire process. It doesn't change between materials. So frequency 1 equals frequency 2. Those cancel out. And you get that n equals lambda 1 over lambda 2. You know that the index of refraction inside the thin film is 1.38, which equals lambda 1, 550, over lambda 2. So you need to do 550 divided by 1.38, which gets you about 398 nanometers. And you could, if you wanted to, change all of that to times 10 to the negative 9th meters. I like leaving it in nanometers. All right, so that's going to be your wavelength 2, which you plug into that guy there. So we end up with, let me make this all smaller again. You end up with 2t equals m, which is any integer, plus a half, times lambda 2, which is 398. And all you have to do to solve for t here is figure out what to use for m. And we're looking for the thinnest film, the minimal one. So you need to find the number that will minimize this equation. And without looking at it too hard, you could say m equals 0 to get 2t equals 1/2 times 398. You couldn't do m equals like negative 1 or something because you'd end up with a negative thickness, which you definitely can't physically have. So your thickness still has to turn out to be positive. You choose the lowest m so that thickness is still positive and not 0. All right, so all that's left to do is solve this for t. You do 4t equals 398, so divide 398 divided by 4, and that gives you 99.6, and that's nanometers for your thickness. All right, if you guys have any questions, please let me know. I know these problems are a little bit complicated. What I am going to do is have an open Google Meet all during class tomorrow, so you can hop on and ask questions if you would like to, or just chat as you're alone in isolation and quarantine, whatever you need to do. But please let me know if you have questions. Miss you guys a lot. Hope to see you soon. Stay safe.